Hello students, this is Dr. A.S. Sayyed. Today we will discuss problem number 4 on the analysis of continuous beam using steepness matrix method. The highlight of today's problem is the spring support. If a spring support is provided in the beam, how to analyze the beam using steepness matrix method. The statement of problem is analyze the continuous beam using structure approach of steepness matrix method. Take EI constant. If you look at the beam, the left end of the beam is fixed support. Then one simple support is provided at point B. Vertical reaction at point B represent that it is a simple support. And at point C, spring support is provided. Spring is fixed at the bottom. The steepness of spring is given to you. K is equal to EI. This is steepness of spring. You might be knowing spring is having its own steepness, and that K is equal to EI. As far as loading is concerned, AB span is subjected to central point load of 40 kN, and at point B there is an external moment acting in clockwise direction. This is clockwise moment. Magnitude is 30 kN/meter. Question is to analyze the beam using steepness matrix method. All of you know that how to start. What is the first step of solution? First step is to find out degree of kinematic indeterminacy of the given beam. So support A is fixed. We know that kinematic unknowns are 0 at fixed support. Support B is a simple support. So kinematic unknown is only one, and that is rotation. And since spring support is provided at point C, spring support behave like a simple support. It means there will be a rotation theta C. But of course, because of this external load, the spring will get compressed and it will deform vertically downward. So this is compression of spring is called as vertical displacement of point C, which is delta C. So in short, at spring support, there are two kinematic unknowns. At spring support, dki equal to 2, that is theta and delta. Right? This already we have discussed in the previous class. I repeat again, kinematic unknowns are 2 on the spring support. So total kinematic unknowns are 0 plus theta b 1 plus theta c and delta c. Total is 3. dki equal to 3, theta b, theta c and delta c. Then we have to find out the required matrices in the compatibility condition. So we know that very first matrix is AD matrix. AD stands for action corresponding to unknown displacement in the original structure. Action corresponding to unknown displacement in the original structure. So AD matrix will get from the original structure. So to write down AD matrix, there will be 3 elements because dki equal to 3 now. Okay. So first unknown is theta b, second unknown is theta c, third unknown is delta c. So action corresponding to unknown displacement. So action corresponding to theta b is a moment at B. Action corresponding to theta c is a moment at C, and action corresponding to delta is a reaction or vertical point load at C. So in the original structure, we have to see that point B, point C. Is there any external moment is given at point B? If you look at the original structure, is there any moment given at point B? Yes, there is one moment given which is having clockwise nature. Magnitude is 30. So clockwise means minus 30 kN/meter. So first element moment at B is 30, minus 30. If you look at the C point in the original structure, there is no external moment acting at C. So moment at C is 0, second element is 0. Similarly, if you look at the third unknown delta C, corresponding action is reaction at C or vertical point load. Is there any vertical point load at point C? There is no vertical point load, it is 0. So since there is no moment and no vertical point load is given at point C, second and third element of AD is 0. And since external moment acting at point B, it is clockwise in nature, so minus 30 kN/meter is the first element of AD matrix. Okay. Now second vector, we know that we have to find out ADL vector. Stands for action corresponding to unknown displacement in the restraint structure. Restraint. So we have to fix this structure. So for the simplicity, again we have drawn these two members separately. So A, B, then BC, all supports are fixed, right? Now we have to find out the fixed end moments first. So central point load on AB span, fixed end moments are WL by 8. We know that it is WL by 8 plus minus, that is anti-clockwise on left end. So it is plus, clockwise on right end it is minus. Magnitude of this moment is 20. Now since if you look at the given beam, there is no load on the second member, BC member, there is no load. If there is no load, moment is equal to 0. So moment is 0 on the second span because of no load on the member. If there is no moment, even there is no load, reactions are also equal to 0. Both the reactions are equal to 0, right? Now AB span, since if you look at the unknowns, our first unknown is theta B. Corresponding action is moment at B. Second unknown is theta C. Corresponding action is moment at C. And third unknown is delta C. Corresponding action is reaction at C. So we have to find out moment at B, moment at C and reaction at C. We are interested to find out reaction at C only. We are not interested to find out reaction at A and B. So no need to find out reaction at A and B. But if you look at the BC span, we are interested to find out reaction at C. But in BC span, since there is no load, the reaction at C is equal to 0. Okay. So finally, if you want to write down the ADL matrix, again there are three elements corresponding to three unknowns. First unknown is theta B, second unknown is theta C, third unknown is delta C. Action corresponding to theta B is moment at B, action corresponding to theta C is moment at C, and action corresponding to delta C is reaction at C. So what is the moment at B in the given figure? This minus 20 plus 0. Minus 20 plus 0. Total moment is minus 20. What is the moment at C? There is no moment at C. It is 0. So moment at C is 0. As well as if you look at the support C, there is no reaction. RC equal to 0. So moment at C and reaction at C are 0. Moment at B is minus 20. This is ADL matrix. Next we have to derive the stiffness matrix K. To derive the stiffness matrix, we know that we have to give unit displacements one by one. So first there are three unknowns in this figure, theta B, theta C and delta C. So first theta B equal to 1. Give the unit positive rotation at joint B. Positive means anti-clockwise sense. Unit positive rotation at joint B. To rotate the joint B in anti-clockwise sense, we have to apply moment in anti-clockwise sense. So here if you look at the anti-clockwise moment is applied at point B. Okay, this is anti-clockwise. Since B is a common joint to AB and BC member, both the members will be deflect when you apply the moment to rotate joint B. So both the members will deflect. Okay, what is the magnitude of moment required to rotate a joint? Already we have discussed, it is 4 ER by L. 4 ER by L is the moment required to rotate a joint. At near end it is 4 ER by L. At far end it will be 2 ER by L. The joint which we are rotating, it is 4 ER by L. So we are rotating joint B. So it is 4 ER by L at B in both the span and 2 ER by L at far end. That is at A, and at C it is 2 ER by L. If you substitute the value of span is 4 meter for AB. So 4 by 4, it is 1 EI at B, and half of that 2 EI by L means 2 by 4, 0.5 EI at A. Similarly, span of BC is 2 meter. So 4 by 2, it is 2 EI at B. Half of that 2 by 2 is 1 EI at C. Okay. So these are the moments. Now since our unknown, one of the unknown is delta C, corresponding action is reaction at C. So we have to find out reaction at C also. Reaction at C means it will occur in BC member. So no need to find out reaction of AB member. Okay. Now how to find out reaction of BC member? Reaction is in two parts, we know. Reaction due to external load plus reaction due to moment. But since there is no external load in the given beam, we are deriving the stiffness matrix. So we are not considering any external load. Okay. So there will be reaction due to only moments. Only moments. So how to derive the reaction because of moment? Already we had discussed in previous two problems. Reaction due to moment is equal to sum of moment divided by span. Sum of moment, that is 2 EI on the left end, this 2 EI plus 1 EI on the right end. So it is sum of moment 2 EI plus 1 EI divided by span is 2. Span is 2. So what is the answer? This reaction is equal to 3 EI upon 2. It is 1.5 EI. 1.5 EI. Now since this answer is positive, this answer is positive. Why it is positive? Because both the moments are in anti-clockwise nature. If it is anti-clockwise means plus. So 2 EI plus 1 EI, this answer is positive. So positive means it is anti-clockwise in nature. If it is positive, this reaction is positive, that is anti-clockwise. Reaction couple will be of opposite nature, that is clockwise. Clockwise means left upward and right downward. Like this we have to apply the reactions in unlike parallel forces or couple form. So left upward, right downward. This represent the clockwise nature. Okay, understand again. Reaction due to moment is equal to sum of moment divided by span. 2 EI plus 1 EI. Both are anti-clockwise, so positive. So answer is plus 1.5 EI. Plus means it is anti-clockwise. If this answer is anti-clockwise, your reaction couple will be clockwise. Clockwise means left reaction is upward and right reaction is downward. Magnitude of both the reaction is same. So if you look at here, magnitude is 1.5 EI, left upward and right downward. Okay, this is reaction at C. Now based on this, we have to collect the required actions. Our unknowns are theta B, theta C and delta C. These are our three unknowns. Corresponding actions are moment at B, moment at C and reaction at C. Okay, so what is the moment at B? This 1 EI plus 2 EI, total 3 EI. This is moment at B. What is moment at C? Moment at C is 1 EI. This is 1 EI. And what is the reaction at C? Reaction at C is downward. Downward means minus. Magnitude is 1.5. So minus 1.5 EI is the value of reaction. This is first unit displacement figure. Similarly, second unit displacement figure is theta C equal to 1. Give the unit positive rotation at point C. Positive means anti-clockwise again. Now since we have to rotate joint C. C is the end joint of the beam. When you rotate the joint C, there is no effect of this rotation on AB member. Since in previous figure, B was a common joint to AB and BA member, when you rotate joint B, both the members will deflect. But in this case, since we are rotating joint C, its effect will be on only BC member. There is no effect of joint C on AB member. So moments in AB member are 0. Moments in AB member are 0. Now in BC member, since we are rotating joint C, 4 EI by L is moment at C, half of that 2 EI by L at point B. 4. Span of this BC is 2 meter. So 4 upon 2, this is 2 EI. Then 2 EI by L is 2 upon 2, 1 EI. Okay, these are the moments. Now we have to find out the reactions also. Reactions are sum of moment divided by span. So this is 1 EI plus 2 EI. Sum of moment is 3 EI divided by span is 2. So 3 EI upon 2, the answer is 1.5 EI. Okay. Now since this answer is positive because both the moments are anti-clockwise, 3 EI is plus. So divided by 2, this answer is plus 1.5 EI. Plus means anti-clockwise. If this answer is anti-clockwise, reaction couple will be clockwise. So left upward and right downward. Okay, these are the reactions of BC member. Again we have to collect the actions. Our first unknown is theta B, second unknown is theta C, third unknown is delta C. Corresponding actions are moment at B, moment at C and reaction at C. What is the moment at B? It is 0 in AB span and 1 EI. So 0 plus 1 EI. Moment at B is EI. Okay. Then moment at C, it is 2 EI and reaction at C, it is downward minus 1.5 EI. Downward means minus. This is second figure. Now third figure, delta C equal to 1. Third figure is delta C equal to 1. Give the unit positive displacement at point C. Again, when we give the displacement at point C, there will be no effect of this displacement on AB member. Reactions and moments of AB are 0. Okay, only BC member will deflect. We are giving the displacement in positive direction, means that is vertically upward. So upward, if you give the vertical displacement at point C, the moment required to give the vertical displacement, already we have discussed, it is 6 EI by L square. It is same at two ends, even in magnitude as well as nature. Now how to decide the nature of this moment? Draw one arrow in the direction of displacement, like this, vertically upward. Draw one arrow in the direction of displacement and bend that arrow outside the beam. So it will give you clockwise moment. So clockwise at both ends. Clockwise moment. What is the magnitude? 6 EI by L square. L is equal to 2 meter. So 6 EI divided by 2 square means 4. 6 by 4. Answer is 1.5 EI. Okay, clockwise in nature, both at both end it is clockwise. Clockwise 1.5 U at B, clockwise 1.5 U at C. Now to find out the reaction due to this moment, sum of moment 1.5 EI plus 1.5 EI. Since it is a clockwise, it is minus 1.5 U minus 1.5 U. Sum of moment. EI is outside. EI is common. So minus 1.5 U minus 1.5 U. Sum of moment divided by span is 2. Answer is equal to minus 1.5 U EI. Answer is minus 1.5 U EI. That is a reaction. The answer is minus, represent the clockwise. So reaction couple will be anti-clockwise. Anti-clockwise means left downward, right upward. This is anti-clockwise. Okay. So look at this. It is left downward and right upward, represent the anti-clockwise couple. Remember this minus sign we have used to decide the nature of couple of reaction. So once, because of this minus, we have decided it is anti-clockwise couple. Then don't write down this minus again here. It is simply 1.5 EI. Reaction magnitude is 1.5 EI. Okay, that minus is not taken into account. It is already taken into account to decide the nature of couple. Okay, so like this we have to find out the reaction. Again, finally we have to collect the actions corresponding to unknown displacement. So first unknown is theta B, theta C second unknown, and delta C third unknown. So action corresponding to theta B is moment at B. Moment at B, it is 0 at B in first span, and clockwise moment means minus 1.5 EI. So answer is minus 1.5 EI. Then moment at C, again clockwise 1.5 means minus 1.5 EI. And reaction at C. Reaction at C is, now this is upward 1.5. Upward 1.5 EI. Okay, this is the reaction because of moment. Now remember that at point C, spring support is provided. Now when spring support is provided, the steepness of spring is taken into account at this figure when delta C equal to 1, because when you provide the spring support at any point, because of this spring support, which displacement kinematic unknown is additional or additionally added in the at the point, and that is deformation or displacement of spring. Otherwise, if you replace this spring support by a simple support, it may be hinge or roller. Theta is kinematic unknown, but because of replacing this hinge or roller because of spring support, the additional kinematic unknown is delta C, because in both the cases there is a rotation theta. But because of spring is having ability to compress, the unknown which is added because of spring is delta. And that's why the steepness of spring is added in the figure delta C equal to 1. Okay, please understand, the steepness of spring is added in the figure delta C equal to 1. But in which element now? In which element it is added? So it is added in the element corresponding to unknown delta C. This is added in the action corresponding to delta C. So this will be added in delta C element. Understand? So where the steepness of spring is taken into account? Steepness of spring is taken into account figure delta C equal to 1 and element delta C. So now initially it is 1.5 EI reaction, plus we have to add steepness of spring which is given to you EI in the original data. In the original figure it is written K equal to EI of spring. So total reaction now, see here, this is 1.5 and plus this vertical reaction is steepness of spring. Spring force is added in the reaction at C. So total 1.5 EI plus 1 EI, it is 2.5 EI. Okay. So if you remove this spring support by a simple support in this problem, then it will be only 1.5. It will be only 1.5. But since spring support is provided here, this 1.5 plus steepness of spring is 1 EI. So total is 2.5 EI. And that's why this element is 2.5 EI. Okay, 1.5 plus 1 EI. So like this you can finish the steepness matrix now. I'll repeat again. The last element, this element in the delta C equal to 1 figure and in the element corresponding to delta C. In this combination, the steepness of spring is added. Since spring is provided at point C, it will be added in the figure delta C equal to 1. And since spring is having ability to compress, so delta C unknown is increased because of spring only. It is added in the element corresponding to delta C. So this 2.5 we have obtained by 1.5 EI is the reaction due to moment actually, and then here we have added 1 EI is a steepness of spring, and that's why this total answer is 2.5 EI. Okay. So this is steepness matrix. First column from theta B equal to 1, second column from theta C equal to 1, third column from delta C equal to 1. First unknown is moment at B, then second is moment at C, and third is reaction at C. These are the action corresponding to unknown theta B, theta C and delta C. So in three figures we have taken moment at B, moment at C and reaction at C. Okay. Now once you find out steepness matrix, next is using compatibility condition or equation of equilibrium AD equal to ADL plus K into D. We can find out the unknowns. Okay. So this theta B equal to minus 4.782 upon EI, delta C is minus 2.608 and theta C is equal to 0.434 upon EI. Okay. Now once we find out this displacement, we can find out the moments by using moment equation. AM is equal to vector of unknown moments. Okay. So already we have discussed in three problems. Since beam having two span, AB, BC. So moments are at AB, A to B, B to A, B to C and C to B. There are four moments. Spring support is behave like a simple support finally. So simple support means moment must be equal to 0. This condition should validate in the calculation also. Okay. So there are four moments MAB, BA, BC and CB. AML vector, we know that AML stands for values of these four unknown moments in the restraint structure figure. So this plus 20, minus 20, 0, 0 is taken from the restraint moment figure, second step. AMD, values of all these unknown four moments in the unit load figures. Now since in this problem there are three kinematic unknowns, there are three unit load figures, theta B equal to 1, theta C equal to 1 and delta C equal to 1. And that's why in AMD matrix there are three columns. Three columns because three unit load figure, three kinematic unknowns. Okay. And these elements are nothing but this is MAB, BA, BC and CB in this figure theta B equal to 1. This is MAB, BA, BC and CB in theta C equal to 1. Similarly, these are the four moments in delta C equal to 1. D is equal to values of your unknowns which are known to you now. In previous step we have calculated, put all those values of theta B, theta C and delta C. 1 upon EI is taken outside. This EI and this EI will get cancelled. And now if you solve this matrix, you will get the answers of MAB, BA, BC and CB. So here you will get CB is equal to 0. Okay. Finally, you can plot the bending moment diagram. So bending moment diagram, first simple moment, that is positive moment. First span is subjected to central point load. So let it be, this is point A, this is point B and point C. So first span is central point load, so moment is triangular in nature. There is no moment on the second part because there is no load. Okay. Now moment AB, MAB is equal to anti-clockwise 17.60, so it must be upward 17.60. Okay, this is 17.60 anti-clockwise. BA is equal to clockwise 24, B2A clockwise means upward, so it is upward 24.78, and B2C is also clockwise -5, clockwise means it is downward. Now here it is downward 5.218. Okay, and at point C it is 0. So understand now, since in the original figure at point B clockwise 30 moment is acting, clockwise 30 kilonewton moment is acting, the whatever two moments we are getting here, BA and BC, this BA plus BC must be equal to that 30 moment. This is the check you can verify. Minus 24.78 and minus 5 point, the answer sum of this is minus 30. It is 0. Okay, so at point C it is 0. So now how to join this? This is the point which you have to join. So this is your final bending moment diagram. If you want, you can highlight the net bending moment diagram. This is net bending moment diagram. Okay, like this. So like this you can solve the problem of analysis of continuous beam using stiffness matrix method if spring support is provided in the beam. So spring support means stiffness of spring we have to take into account. In which element stiffness of spring will come in picture? Stiffness of spring will added in the figure of delta equal to 1. Okay, and the element corresponding to delta, that is R. Here we have to take it. If you understand this, then rest of the problem is similar to previous problems. Okay, so thank you. This is fourth problem on the analysis of beam using stiffness matrix method. We'll take last problem in the next class on the internal joint, internal hinge provided in the beam. Okay, thank you very much.